Welcome everyone, and thanks for being here for the first installment of the Ithaca Fest for 2022. As most of you know, this is it's a recurring seminar for everything that involves category theory, and we're building this community around it. And I will post useful information in the chat as the website, and also let me say that we have seminars scheduled until November for this year, excluding the summer break. And so instead of just listing all the participants, I will just post a link so that you can go and see whoever will be giving a talk for the rest of the year. And we also have another initiative, which is that of a book on category theory. And I think maybe Fosco can say a few words about it before we start with the talk.
Yes, thanks, Eduardo. Actually, yes, Ithaca doesn't stop at the fest that you are about to see. Another important thing that we do is to reach out to more people and to help our fellow students we organize a course on category theory that you can see on the YouTube channel of Ithaca. If everything goes as planned from the course, at some point we will write a book based on the lectures that we are giving. So at some point we might appear in your libraries. We are very happy to see you, especially in the Zulip channel that we built over the course. Everyone who has questions related to the category theory they are learning is welcome to join us and to ask them. It doesn't matter if they are not related to the course, to the lectures, to the order of the presentations that you see. We are eager to respond to your questions. Let me add that I'm not alone in this. Many other people are helping with the project. Some of these are here: Greta, Jacopo, Enrico, Daniele, but there are many other people that are helping with this project, and we really believe we are doing something good. So join us and check it out.
Okay, thanks Fosco for that. So I think we can start with our first talk. So the first speaker for the day is Antonio Lorenzin with a talk entitled Formality and Strongly Unique Enhancements.
Hello everyone, can I share my screen? Let's see. Okay. So should I start?
Yes, please go ahead.
Okay. Okay, so today I will talk about formality and strongly unique enhancements. I will very much like to thank all the Ithaca organizers for letting me talk or have the possibility to talk again. And okay, so in this talk we will deal with algebraic triangulated categories. So we will start with some preliminaries about it, and then we will move on to the main notion, a new notion that I defined, which is triangulated formality, which is a generalization from intrinsic formality of graded rings. And we will see how this relates to enhancements, uniqueness of enhancements. And then we will state our main result, which we will then apply to homotopy category of complexes and derived categories. Okay. First of all, let me say that little k will be a commutative ring, and all categories will be k-linear in this talk. And I also should say that all categories are small in an appropriate Grothendieck universe. Okay, so first of all, what is a triangulated category? Well, category T is called triangulated if it is an additive category equipped with an autoequivalence, which is called the shift. And we also have a class of distinguished triangles, which are written as you see. You have A, B, C, and then the shifted A. And this distinguished triangle need to satisfy some actions. I don't want to go into details, but I want to state some very important properties. So if we have a morphism, what we can do is we can get a distinguished triangle completing the morphism. So the first one is the morphism, then we have this C added to it, which is determined up to isomorphism. So what we can do is we can call it the cone of the morphism. Roughly speaking, the idea is that triangulated categories are similar to abelian ones, meaning that we are replacing kernels and cokernels with the notion of cone. However, the cone is not functorial. So in particular, C is determined up to isomorphism, but that isomorphism is not unique in general. Another property you may expect, as for kernels and cokernels, if you have a commutative square, then you can extend it to a map of distinguished triangles. And this, because the cone is not functorial, is done in a not necessarily unique way. Okay. When we talk about categories, we want to talk also about the functors. And in this case, the functors are just the one someone may expect, meaning that they have to preserve the structure. So the triangulated category is additive. So F is additive as well. It has to commute with the shift functors. So it does so via natural isomorphism eta. And of course, F sends distinguished triangles to distinguished triangles. And it does so using the natural isomorphism eta. When we have such a functor, we call it triangulated. Some call it also exact, as for the functors between abelian categories. I should also say that sometimes we will use F eta to emphasize the role of the natural isomorphism. And we will need this in a slide. We will get to it. Okay, let me give you some examples. The main examples of the theory are all linked to chain complexes. So what is a chain complex? Well, it's a graded module with a differential. So at every step, we have a module or an object of our category, and we have a gradient over Z, these in the integers, and the composition of two consecutive maps will give 0. And we say that our chain complex is bounded if eventually we reach 0, both on the left and on the right. So the first example of triangulated category is the following. If we have any additive category A, we can consider the bounded homotopy category of complexes, which has as objects chain complexes, which are bounded for us. And the maps are chain maps up to chain homotopy. If you don't know what chain homotopy is, just think about homotopy. In fact, the definition, follows from algebraic topology, thinking about the homology chain complex. Okay, another very meaningful example is the one of derived categories. So given an abelian category A, we define the bounded derived category dB of A, whose the objects as before are chain complexes, but the morphisms, well, are hard to describe. They are a roof or a span, if you want. What I can say about this is that the triangulated structure we are equipping this category is such that if we have a short exact sequence on A, we get a distinguished triangle on the derived category. And so KB of A and dB of A are our very key and important examples. And in fact, they are not only examples of triangulated categories, but they are also algebraic. And so now let me talk about what algebraic means. In order to do so, we need to talk about DG categories. So other definitions are coming. A DG category is a category C enriched in chain complexes of K modules. I want to recall that K is a commutative ring. And what does that mean? It means that all the omsets are chain complexes, and the composition is a morphism respecting the DG structure. So it commutes with the differential and also with the grading. The main thing we are interested about is the homotopy category associated to a DG category, which is H0 of C, and has the same objects of our DG category, but the morphisms are just the homology of it. So kernel of D0 over the image of the -1. Instead of the homotopy category, we can also study the graded homotopy category, which is actually the same, but we are now considering all the homologies. Okay. The important part about DG categories is that we can define the DG version of shifts and cones, and in fact, in this setting, they become functorial. So we are very happy because now we can get many more results than the ones we can with only triangulated categories. So let me talk about a pre-triangulated DG category, which is just a DG category C closed under the cones and the shifts in the DG world. And under these assumptions, H0 of C, so the homotopy category, is a triangulated category in a natural way. And this behaves as you may expect, meaning that the DG shifts become shifts and the DG cones becomes cones. And now a very, very important thing is that if we pick any DG category, then we can describe the pre-triangulated closure, which is determined uniquely up to DG equivalence. We will see what a DG functor is in a moment. And we can now denote TR of C, the triangulated category associated to C, which is just the homotopy category of the triangulated closure. We will see that this uniqueness is proper of the DG world, because if we think about triangulated categories, well, they can have the same generating set, but that generating set can give you different triangulated structures. Okay. So now that we know what DG categories are, let me talk about DG functors. Well, a DG functor is a functor F between, of course, two DG categories. And in fact, it just behaves accordingly to the DG structure. So it is a morphism of degree 0 and it commutes with the differential. Another very, very important thing is that if we have a DG functor between two DG categories, then we have a unique extension on the pre-triangulated closures. And also, given a functor F between pre-triangulated categories, a DG functor, then we have a triangulated functor on the homotopy categories. And this is very important. I should also note that having an extension is of course, another property of the DG world and not of the triangulated categories in general, and the uniqueness as well. So now that we have all this machinery, we can say that a DG enhancement of a triangulated category T is a couple CE, where C is a triangulated DG category, and E is just a triangulated equivalence between the homotopy category of our pre-triangulated DG category and T. And now if T admits a DG enhancement, it is algebraic. So to say, we can study the triangulated category via DG categories. And so, in a sense, we can restore functoriality when we are dealing with algebraic triangulated categories. But first question that someone may ask is, can we do it in a unique way? And what does it mean? In order to answer to this question, we need to talk about uniqueness of DG enhancements. So a DG functor between triangulated DG categories is a quasi-equivalence if the homotopy functor associated is a triangulated equivalence. And now what can we do? Well, an algebraic triangulated category T as a unique DG enhancement if for any two enhancements C and C prime E prime, we can find a zigzag of quasi-equivalences moving from C to C prime. And of course, all these DG categories here will be triangulated, and they will in fact give an enhancement of our triangulated category. So now we can move on and talk about triangulated formality. I should say that this definition will be given afterwards, because first of all, I want to talk about a motivating example. And the motivating example is the category of finite dimensional vector spaces over a field, of course, K. And this category has a triangulated structure by setting the shift functor to be the identity and the distinguished triangles to be generated by the short exact sequences. We have this very important theorem by Schlichting saying that if we consider K to be the finite field with the P elements and P prime, then K mod has two enhancements, and these two enhancements are associated to Z over P squared Z and FP epsilon over epsilon squared. And these two enhancements do not admit a zigzag of quasi-equivalences. So in particular, K mod does not have a unique enhancement. And so we also have an example of an algebraic triangulated category which does not admit a unique enhancement. And what we can see about these enhancements is that the one associated to Z over P squared Z is in fact Z linear, but it is not linear over the field. So a natural question to ask is, what about uniqueness of enhancements for K linearity? In order to address this question, I found this notion, which is intrinsic formality for graded rings. So first of all, let me say what a formal DG ring is. Well, first of all, a DG ring for us is just a DG category with one object. And then we can say that A is formal if there exists a zigzag of quasi-isomorphisms moving A to its graded homotopy, which is just a graded ring. And well, what are quasi-isomorphisms? Well, they are morphisms preserving the graded homotopy. Here I'm using the notions concerning DG categories, but if you already know what a DG ring or a DG algebra is, this is generally the homology. And so now what we can say is that a graded ring B is intrinsically formal if any DG ring A having as graded homotopy B is formal. And so to say, every time we start with something having as graded homotopy B, we can always find this kind of zigzag. And this is very, very similar to uniqueness of enhancements. So our idea is to try and use intrinsic formality to prove the uniqueness of enhancements. So first of all, if we have an enhancement CE of K mod, then what we can consider is the object in C, which is the pre-image of the field K in K mod. And now what we can see is that its graded homotopy is KTT minus 1 with T of degree 1. And so the idea is that if this graded ring is intrinsically formal, then the enhancement is unique. And we can show this by using the same zigzag we had for the definition of intrinsic formality. And then we have this other quasi-equivalence, which is given by the inclusion. And then we can extend it because we can use the pre-triangulated closure. And as a matter of fact, we are able to prove that KTT minus 1 is intrinsically formal. And so K mod has a unique K-linear enhancement. But now one may wonder if this is very much about KTT minus 1 or if it does hold for all the graded rings. And the answer is that this procedure is in fact general. So what we have is that B, for every B intrinsically formal graded ring, we can pick any enhancement CE of the RB, and we get a zigzag of quasi-equivalences moving from the pre-triangulated closure of B to C, and we can do so also fixing the only objects of B. And this is, well, if you look at how we choose A, so that it goes to K, well, this means that when we move, we get exactly in the same identical object when we look below in the triangulated category. So we have this fixed property, which is something more than uniqueness of enhancements. So we can generalize this idea and talk about the G categories, which are triangulated formal. And so it is triangulated formal if for every enhancement CE of the triangulated category associated to A, we have a zigzag of quasi-equivalences moving from the pre-triangulated closure of A to C, and also we require that it fixes all the objects inside of A. First, let me tell the slogan of triangulated formal categories. They are somewhat fixed at the homotopy level, because for every enhancement we have, we can in fact fix all the objects inside of our DG category. And as a little remark, if A is a triangulated formal, then the triangulated category associated to A has a unique enhancement. And also we can say something more. The pre-triangulated closure of A is triangulated formal if and only if the triangulated category associated to A has a semi-strongly unique enhancement. I will give the definition of a semi-strongly unique enhancement in a second. First, let me say that these two things help us understand that triangulated formality is not something that should be very strange for someone in the theory, because we are just moving between notions of uniqueness of enhancements. And okay, so now let me talk about strongly unique enhancements, and so also of semi-strongly unique enhancements. So an algebraic triangulated category T has a strongly unique enhancements if given two enhancements CE and C prime E prime, we still have a zigzag of quasi-equivalences F as before, but now we require that this diagram, commutative diagram, holds up to natural isomorphism. In the same fashion, we can define semi-strongly unique enhancements. And in this case, we require this to commute but only for objects. So this is not a natural isomorphism. Okay. So now some questions about enhancements. And a first question that someone may think about is, are there examples of non-algebraic triangulated categories? And the answer is yes. There is a paper by Murosh, Ueda, and Strickland talking about a somewhat simple example. And we, in fact, know very little about non-algebraic triangulated categories, but there are a few examples. And it is important to notice that we only have one when we require linearity over a field, and that is given by Rizzardo and van den Berg. Another question that may arise is, are there algebraic triangulated categories with a non-unique enhancement? And the answer is still yes. As we saw, the category of finite dimensional vector spaces, but also the category of vector spaces in general, are an example of algebraic triangulated categories with a non-unique enhancement. And so another question that may arise is, are there algebraic triangulated categories having a unique enhancement, but not a strongly unique enhancement? And the answer to this question is that we do not know yet. And it seems to be a very hard task to answer. So I tried to look in this way, but I haven't come up with an example of it. So my idea was to try to characterize what the requirement of being strongly unique. And more precisely, the question is can we find some property to characterize the strongly unique enhancements of the triangulated category associated to A when A is a triangulated formal DG category? And the answer to this question is yes, as we will see, in fact, is our main result. But first of all, we need some other definitions. First, let me say what a graded restriction is. So let A be a DG category and consider a triangulated equivalence, F eta, from the triangulated category associated to A. Okay, and we require that F fixes all the objects in the graded in the homotopy category associated to A. And now what we can do is that we can associate an isomorphism, which is called the graded restriction. Well, this is not an isomorphism, sorry, this is an equivalence, a graded equivalence, I should say. And okay, how can we do this? Well, first of all, let me say also that since the DG category is not necessarily pre-triangulated, this is generally bigger than the homotopy category. So now we are just interested in the one in the graded homotopy category. And what we do, well, we just, for the objects, we are just fixing it. And then on morphisms, we use F and eta to define it. We have some natural isomorphisms between the homes and this direct sum. And now we can move using first F and then our natural isomorphism eta, and then go back to the to the omsets in the graded homotopy category. And so in this way, we get this graded restriction. If you are afraid of this diagram, I can understand it. It's not really important to get it. We will see how this applies when we are working with homotopy categories of complexes and derived categories. But this is very, very important to try and fix all the functors in our triangulated category we are studying. So we say that a DG category A is formally standard if for any two functors f and g, which satisfy this requirement, so they fix all the objects in our homotopy category. So now we can talk about graded restrictions, and we require the graded restriction to be natural isomorphic. Then we can in fact extend it to a natural isomorphism to the two functors, which is not said a priori because we have more objects. We have the cones, and we have the cones we need to know how to deal with. So in a sense, roughly speaking, formally standard categories fix the homotopy level. Also, we said that triangulated formal categories are fixed at the homotopy level. So when we consider this together, we should expect that the homotopy level and the DG level behave accordingly. But in fact, this is not always the case. And so this is the reason why I wrote should, because we need something more in order for it to work. And in fact, in order to get a characterization, we need to study only graded categories. So we are dealing with the DG categories where the differential is actually 0. And in this case, we have that the following are equivalent. So B is triangulated formal and formally standard if and only if the triangulated category associated to B has a strongly unique enhancement. We actually can prove something more for some peculiar DG categories. We can prove that the first one implies the second one, but in fact, it is very hard to go from the second one to the first one. And okay, so what's new about this theorem is that until now, the theory was focused on proving results only for linearity over a field and in very specific cases, while this theorem holds for any k-linear graded category, and k is just a commutative ring. So for any linearity we are thinking about, we can always have this theorem to work with. And so now we will move on and see the applications. And applications are associated to these two notions that are given on homotopy category of complexes and derived categories. And these two notions are in fact given by Xiao Wu Chen and Yu Ye. So let me state them. An additive category A is K-standard if for every triangulated autoequivalence F from the autoequivalence F on the homotopy category of complexes, the following holds. Whenever we have that F sends the additive category to itself, and we have also natural isomorphism such that the restriction of F to A is natural. We have a natural isomorphism between the restriction of F to A and the identity. Well, then we can extend it to a natural isomorphism between the triangulated equivalence and the identity on the whole triangulated category. The same can be done for derived categories. So an abelian category A is the standard if the same property holds for every triangulated autoequivalence F, moving from the derived category of A to the derived category of A. And if you think maybe about the gradient restriction, it should not come as a surprise that, in fact, these two notions are specialized versions of formal standardness. So an additive category A is K-standard if and only if it is formally standard. And this is done because the triangulated category associated to A, which does exist because an additive category is also a graded category concentrated in degree 0. and so it is also a DG category. So this triangulated category associated is in fact equivalent to the bounded homotopy category of complexes, and this holds for all additive categories. And also for the standardness, we have that an abelian category A is the standard if and only if a certain associated DG category is formally standard. And while in the first example, so for case standardness, we have an additive category. So we are working with a graded category, so we can use the theorem. Here we cannot use it because this DG category is very much DG. It has a non-trivial differential. So we will see what happens in that case. But first, let me talk about the bounded homotopy category of complexes. Well, as I said before, we have this equivalence, and in fact, we can obtain that the bounded homotopy category of complexes has a semi-strongly unique enhancement. I should point out that this has never been written explicitly in the literature, but it follows immediately from a previous result of Lorenzin and Orlov in a well-celebrated article that I'm going to discuss also in the last few slides. And so since we have that this has a semi-strongly unique enhancement, we also have that A is always triangulated formal. So in fact, we have that an additive category A is case standard if and only if the bounded homotopy category of complexes has a strongly unique enhancement. And concerning the case of bounded derived categories, we have a very interesting result of Canonico, Niemann, and Stellari, saying that all the derived categories has a unique enhancement, and in particular, the bounded derived category of an abelian category A has a semi-strongly unique enhancement. So, as before, this says that the certain associated DG category we are studying is also triangulated formal. So now what we can do is that we can say that if an abelian category A is the standard, then the bounded derived category of A has a strongly unique enhancement. The converse implication does not hold, I don't know if it holds in general, but I was able to prove it under some finiteness condition. And well, in particular, using this corollary, we have that if an abelian category is hereditary, meaning that all the X groups are trivial for n greater or equal than 2, then we have that the bounded derived category has a strongly unique enhancement. And for as an instance of this corollary of the corollary, we have that the category of the bounded derived category of the category of finitely generated Z modules is hereditary. Has a strongly unique enhancement. Sorry. Okay. Other examples. Another result, sorry, is the following. We can move from case standardness to the standardness, and this is our result of Chen and Yi, and we can do so in the following way. If we have an abelian category with enough projectives, then the homotopy category, then if the homotopy category of the projectives has a strongly unique enhancement, then the bounded derived category of A has a strongly unique enhancement. And this is very, very interesting because in general, it is very hard to move between different triangulated categories and prove that the strongly unique enhancement still holds. Other very important examples are given by the geometric cases. So we have that the bounded derived category of the coherent shifts over on X as a strongly unique enhancement if X is a projective variety over a field whose maximal torsion subshift of dimension 0 is trivial. If you don't know what this means, because this is very geometric requirement, well, you can just think about smooth projective varieties. And this is a very well-known theorem and well-known result of Lund and Orlov in the theory. And in fact, there are various articles using the same identical idea to extend the result. And for instance, Hollander proved that the same thing holds also if X is a smooth and proper variety of dimension greater than 1 over a field. And now, in fact, what happens is that these proofs first show the standardness in order to conclude that the bounded Drake category has a strongly unique enhancement. And so, as a matter of fact, we can extend the generality in which the methods that are used can work. In order to do so, there's another article by Canonico and Stellari. And in this article, they deal with coherent shifts supported on a projective scheme, but now we are working on a quasi-projective scheme. And in order to address that setting, they had to define a new way, and not only thinking about the notion that Lund and Orlov considered. So they defined what are the quasi-ample sets. Given an abelian category A, and let me just say that a quasi-ample set is something that resembles the idea of ample line bundles on a projective variety, on a smooth projective variety. So what happens is that we have these objects, and with these objects, we can surject on all the other objects, and also we can do so without going back. So we have an epimorphism from this direct sum to A, but A does not go to this direct sum. And using exactly what Lund and Orlov did with some adjustments as for the article by Canonico and Stellari, we are actually able to say that if an abelian category A admits a quasi-ample set, then the bounded Drake category of A has a strongly unique enhancement. Thank you for your attention. These are some references, and if you have any questions, please feel free to ask. I hope it was a nice talk, because I'm feeling my fever going up.
Thanks for the talk, Antonio. Are there any questions? We have some time for questions before the next talk. So if you have any, just please don't hesitate to ask.
I would have a couple of questions if nobody has. Okay, so I have two questions. So the first one is, so the notion of formality seems very restrictive to me, especially when I look at abelian categories in general. What kind of intuition should I have? So, like, for example, mod A for A ring in general is not formal, right?
Yeah, formal. Well, I should say that, for instance, all the rings are intrinsically formal graded rings. Mm-hmm. So when you are dealing with something that is concentrated in a degree, it's very trivial. So first of all, that is something to keep in mind. When we are dealing with abelian categories, In fact, we are also thinking about all the X groups and the sequences that they generate. And in that case, it becomes kind of messy. So what happens is that we have this very, very interesting theorem by Canonico, Niemann, and Stellari, telling us that all derived categories are have in fact a unique enhancement. And in the case of bounded derived categories, we have that they have a semi-strongly unique enhancement. This has not been done in anything that resembles what I said today. But if you are interested in that part, I very much suggest you go and take a look at this article, because before this one, we knew the uniqueness of enhancements only for derived categories of Grothendieck categories, or the coherent shifts over a special scheme. So it is a very, very important result for us to get our corollaries on the bounded derived categories. And yes, abelian categories are very, very hard in this sense.
Thank you. And then my second question is, so just to build vocabulary between different languages, what is the infinity correspondent of having unique enhancement? How do we understand it?
I don't know much about the infinity categories, so I don't really know how you can extend it. I should say that there is an article by Antio talking about uniqueness of enhancements for derived categories when we are dealing with enhancements over infinity categories. But I don't know if there is something like semi-strongly unique enhancements and strongly unique enhancements. So that's something to keep in mind. Also, I will add something to your previous question. When we consider this property here to define what triangulated formal category are, well, let me say that this property holds for intrinsically formal graded rings, but it can hold also for other things, because even if you have different formal DG rings, even if you have DG rings that are not formal over B, the triangulated category can be different as well. And so in that case, you may have something, you may have this property even if you don't have intrinsically formal graded rings.
Thank you.
Thank you for the nice questions.
Thanks for the answer, Antonio. Are there other questions? Okay, if not, I think we can silently thank the speaker again, and perhaps take a 5-minute break, since the talk is scheduled at 4, so we can resume in 5 minutes and start again with the next talk. We'll announce it when it's time.